Hi, so welcome back guys. Last time, we looked at that earliest finish time, the pseudocode of it, and we started to set up this formal framework that's hopefully going to allow us to prove that EFT, earliest finish time, is a correct greedy algorithm for the job scheduling problem. Okay, well, I alluded to it last time, but basically we're going to use some kind of inductive proof to show that this is correct, and if we can prove this theorem correct, that implies that EFT is a correct greedy algorithm, meaning that it will always return an optimal solution. Well, how do we do a proof by induction? Well, hopefully you remember from your past courses. I assume that you've taken a course that's shown you induction. If not, maybe go watch a couple other videos or just do some Googling around. Anyways, there's three basic steps. What's the first step? Prove the base case. The second step, assume the inductive hypothesis. What do I mean by that? Well, we have this theorem, and what it's going to boil down to is we're trying to prove that there exists an optimal solution that agrees with our partial greedy solution for all n. Well, I'm going to assume that that's true for I minus 1. So I'm going to say assume I don't know why I put a capital T on that. Small little things, eh? Itch at ya. Assume the inductive hypothesis. And what do I mean here? Well, we're going to assume there exists an optimal solution which agrees with my partial greedy solution after the first I minus 1 decisions or choices. Now, depending on how you learned induction, you might say assume it for I and then prove it for I plus 1, or assume it for I minus 1 and prove it for I. It's the same thing, really. It doesn't matter. But the third step is, well, this is the inductive hypothesis, but we assume inductive hypothesis and prove there exists an optimal solution Now, I could write, oh, you know what? I didn't even write J star here, so I'm just gonna leave that off. I'm giving it a little bit away, but don't worry about that. So there exists an optimal solution which agrees with JGI. So we've assumed that there exists we've assumed that there exists an optimal solution which agrees with JGI minus 1. Then we're going to assume that and try to prove that then there also exists an optimal solution which agrees with JGI. So if there's an optimal solution that agrees with, our greedy solution's I minus 1 first choices, then there exists an optimal solution that agrees with our greedy solution's first I choices, where choice is to include or exclude a job. Okay, well, first, before we get to these two steps, we got to prove the base case. Well, what's the base case? Well, we need there to be, show there exists an optimal solution which agrees with JG0. That's our base case. Well, what does JG0 equal? Remember, this is our greedy solution, partial greedy solution, after it's made I choices, where I equals 0 here. So this is the greedy solution after it's made 0 choices. Remember, if you go back to the previous video with the pseudocode, we could also think of it as JG after I iterations of our for loop. Well, if it's 0, that means we haven't entered the for loop yet. So that means if it hasn't made any choices, it's just the empty set. Now, you might have to check your, your discrete math definitions and whatnot. I'll tell you right now, any set trivially, there's a second I think, trivially agrees with the empty set. You can kind of dig around and fool around with these, definitions over here. Essentially what it boils down to is what you'll find is you're doing a for all over an empty range. When you do any iterator over an empty range, you default to the operator's identity. The operator in question for all is the logical and the identity of and is true. Therefore, this defaults to true, so it trivially agrees. That's kind of maybe more math than what you need to understand it. I mean, that's what it boils down to over here. Or you can just trust me, okay? It does trivially agree. And it's because the empty range of for all boils out to be true over the empty range, which is the empty set here. Okay, good. So the base case is true. But now we get to the actual, meat and potatoes of the proof. I have to really do step 3. So I'm going to assume the inductive hypothesis and try to prove that there exists an optimal schedule, an optimal solution, which agrees with my greedy solution after I choices, assuming that there exists an optimal solution that agrees with the first I minus 1 from the inductive hypothesis. Okay. Well, if it agrees with the first I minus 1, we can really just zone in on the ith choice of the greedy algorithm of earliest finish time. And there's really only 4 cases that can happen. So if they've done the exact same thing for the first I minus 1 jobs, we look at the ith job. Well, our greedy solution, our EFT, can either exclude or include that ith job. And our optimal solution, J star, which agrees with the first I minus 1 choices from our inductive hypothesis, it also has that same choice. It might just happen to exclude or include the ith job. So let's write those cases out. So case number 1, JGI includes JI, and J star includes JI. And when I say includes, excludes, I really just mean, kind of like a plain English interpretation for is element of, is not element of. But hopefully you can break through that barrier. That's case 1. What might case 2 look like? Well, same thing, except maybe J star excludes this here. Excludes the job. Okay. Well, of course, we have the case where we exclude the job. Our greedy solution does, and this one includes. And of course, hopefully this isn't any big shock to you, upper year computer science students or software engineers, whatever. This one's going to exclude it. So we're just going to brute force these cases. So basically we have include, exclude, exclude, includes, excludes, excludes. And remember, we're trying to show that there exists an optimal solution that agrees with our greedy solution. Well, two of these cases right off the bat, and I should say these cases are exhaustive, right? So one of these four things has to happen. So if we can basically show that in all four of these cases the theorem holds, or on the flip side that some of these cases absolutely cannot happen, then we've proven the theorem correct. This is exhaustive, okay? But two of these cases should be, borderline trivial, if not flat out trivial. And why is that? Well, look at 1 and 4. So we know that J star agrees with the first I minus 1 choices. How do we know that? Well, from the inductive hypothesis. That's what we're assuming. So if we know that it agrees with the first I minus 1 choices, and we show that it agrees with the ith choice, that means it agrees with the first I choices. And that's what we're trying to show with this theorem. Look right here. Okay. Well, hold up. We already know it agrees with the I minus 1, and it agrees in this case where they both include it, and it agrees in this case where they both exclude it. So 1 and 4 hold trivially. Well, just hold, yeah, I guess trivially. I don't like to throw that word around, trivially, in case, one student doesn't quite get it, and it makes them feel bad. It's like, oh, it's trivial. Are you stupid? No, not everyone. I mean, it isn't quite trivial, but it's almost trivial. I'll write trivially, though. No offense. I can't think of another word besides trivially. Easily, obviously is almost like, it's obvious. Why can't you get it, right? But yeah, we'll say trivially for now. Okay. Well, that gets rid of these two cases. So we just have to take care of 2 and 3. Now, I kind of touched on this a little bit. There's two ways to take care of these cases. Well, first of all, it's somewhat obvious that, they're at least disagreeing on that ith choice. Well, one thing we can do to show or take care of that, like it looks like, oh, well, it's disagreeing here, therefore the theorem's not holding. Well, if we show that these cases never happen, then we've actually taken care of the problem. Because you say, okay, well, I'm not saying this is true, but if we say 2 and 3 never happen, therefore 1 or 4 always has to happen, well, then the thing holds because 1 or 4 always happens, and those prove the theorem trivially. Okay. So can we show that 2 and 3 never happen? And when I say never happen, basically, if this is true, or if you assume this, you can show a contradiction. If you can do that, then you can show that this case will never happen. And I want to zone in on case 3. Okay. Case 3. This is where our greedy solution excludes the ith job, but this so-called optimal solution includes the ith job. And remember, we're also assuming the inductive hypothesis. Well, what has to be true if our greedy solution excludes the ith job? I always forget my S's, man. Crazy. Well, if you go back to the pseudocode, it includes a job and when does it exclude a job? Well, remember, there's that if statement there. And what the greedy solution does is it looks at the ith job and it says, okay, does this particular job conflict with anything I've had previously? If it doesn't, I add it. If it does conflict, it doesn't add it. So that means what? Well, if it excluded it, that means that this ith job must conflict with a job that it previously added. So I can say if j, g, I, or you know what, I'll even write it out a little bit more formally here. If Ji is not an element of Jgi, then Ji conflicts with at least one job in what? Well, in our partial solution after I minus 1 choices. Right? If at the ith choice you don't include the job, that means some job that you've added previously in your I minus 1 choices has a conflict with it. Okay. So Ji conflicts with at least one job. Could conflict with many, could conflict with all, but it definitely conflicts with at least one. But from the inductive hypothesis, all jobs in Jgi minus 1 are also in that optimal set of jobs. Well, hold up, right? And I'm sure some of you, were already here minutes ago, if not longer than that. That means that Ji, this job Ji, also has a conflict with a job in here. Therefore, Ji conflicts with J star. However, J star is an optimal solution. Optimal solutions don't have conflicts. Well, it can't have a conflict in it, and it has a conflict in it. That's a contradiction. Meaning, case 3 never happens. So boom, case 3 is taken care of. Easy. Okay. Well, now all we have to do is come up with a contradiction for case 2, show that case 2 never happens, and then we've proven our theorem. So how are we going to do that? So if we start to look for a contradiction and find one, then we're done. But I'm going to tell you right now, from my experience, this is one of the #1 mistakes students do with these proofs. They start off and they get everything basically up to here, then they go to case 2 and they say, okay, well this one has to be a contradiction because, well, the professor kind of told me that this algorithm's correct, so I know everything has to work out in the proof. And then, they kind of do some hand-wavy stuff, therefore it's a contradiction. Here's the thing. Case 2 doesn't have a contradiction. Huh? What are you talking about? Well, let me show you this. I'll give you a problem instance here. Maybe it looks something like this. And I have job 1, 2, 3, 4. What's J, G, let's say 3. Actually, let's say 2. JG2. What does this look like? So this is my greedy solution after it's made 2 choices. Okay, is it going to include job 1? Well, this is and you'll notice I've ordered this by earliest finish time. So this is the imposed ordering on it after we throw it through that algorithm. Okay, so it includes job 1, yes. Does it include job 2? Yeah, all right, cool. So this is going to be 1, 2. So it's decided to include both of those. Let me give you an optimal solution. J star. And this optimal solution is going to look like this. 1, 3, 4. And we get to the heart of the problem here. So you'll notice, hopefully I've been doing this. I try to be very careful with the way I phrase things. But when I talk about J star, I've always been saying a optimal solution or an optimal solution. I've never been saying the optimal solution or the maximal set, the, maximal set with no conflicts. Why? Well, there can be many, many, many optimal solutions for the same problem instance. For example, this is just 4 jobs, but by my count, there's actually 2 optimal solutions. What are they? Well, this would be, the first one, and the second one is this. 1, 2, 4. Both of those have cardinality 3, none of the jobs conflict. They're both optimal solutions. The optimal solution isn't necessarily unique. Oh. Well, does that cause a problem? Because, the greedy solution's optimal solution might be wildly different from another optimal solution. Well, that's true. And if you go back and look at the theorem we're trying to prove, we're not actually saying that for all optimal solutions it agrees with our greedy solution. We're just showing that there exists at least one optimal solution that agrees with the greedy solution. So it ends up not being an issue, but it does end up being an issue here because, like I said before, this is not a contradiction. Why isn't it a contradiction? Well, just look here. And I'll write JG1. So J star agrees with JG1. It says, okay, you've made one choice. What was the choice? Oh, to include the first job? I agree with you. Okay? Then we get to the second. And you can think of that as the inductive hypothesis, right? For I minus 1 with I equal to 2. Now we start looking at job I. We start looking at job number 2. And our greedy solution says include. Remember, in case 2, the greedy solution is including the ith job. But J star is excluding it. But that's exactly what we have here. And there's no contradiction. This is an optimal solution. This is the greedy solution after 2 choices. But J star doesn't agree with it. It's an optimal solution and it's not agreeing with it. Well, again, that's not a fundamental issue because we're not saying all optimal solutions have to agree with it. There just exists an optimal solution which agrees with it, which there does. You should be able to work that out. So how do we go about proving case 2 or dealing with case 2? Because case 2 can happen. So what do we do? Well, it's not contradiction, so we can't say that just never happens. We can't sweep it under the rug. We gotta, deal with it somehow. So you might say, okay, here's the idea. J star does not agree with it. I get it. It doesn't agree with the ith choice. But here's what I'm going to do. I'm going to create a new solution. And I'll call that solution maybe J prime. And I'm going to base that solution based off of J star. And I'm going to create this J prime in such a way that 2 things are true. So this is going to be such that number 1, J prime agrees with my partial greedy solution, JGI. And number 2, it's not good enough that I've created something that agrees with it. I also have to ensure J star is optimal. Well, that makes sense. If I can show that, look, okay, I know J star has its issues, doesn't agree on the ith choice, so I'm going to kind of take J star I'm not going to build up a new solution from scratch most of the time. I'm going to take J star and I'm going to alter it slightly, massage a few things around. So if I move this job out and take this job in, I get a new solution that now agrees with my greedy solution and is also optimal. And then that'll help us prove the theorem. Okay, so how are we going to do that?